Ashwin, shall we start?
Yes, Nija, we can start.
Okay. So, good evening, everyone. Welcome to the fourth training session of LCBC AlgoQueen 2022. Today, we have with us to take up the session. You can go forward with it, Ashwin.
Hey, hi everyone. So today I'll be doing prime sieve and uh, prime factorization using prime sieve. So uh, is my screen visible?
Yes, Ashwin,
Okay.
but it is blank.
Yeah, it's just a white screen, like so.
Okay, okay, fine,
Yeah.
fine.
Okay. So you can you everyone is familiar with the question like prime or not from the practice round, right? Like the question was given n numbers, like check if each of the numbers is prime or not. What if I ask you to find if like numbers from 1 to n? I give numbers from 1 to n and 1 to n, and I want you to tell me if like all the primes under like n. Suppose like if n is equal to 10, like all the primes under 10 would be 2, 3, 5, 7. This would be the all the primes under like 10, right? 9 is not a prime, 8 is not a prime, obviously 10 is also not a prime. So in such a scenario, like one thing that we can do is we can solve this similar to like find prime or not. Go from each numbers like from 1 to n and check if each of the numbers are prime. If they are prime, we'll include them in our answer. But then, is there a faster way of doing this? So that's the question we'll try to answer today. So, do you think is there a faster way to doing this? You might have learned this in school, uh, but then today we'll be trying to code this like a method to find all the prime numbers less than n, and some other things that we can do with this technique. So do you think we can do it faster? If you think you can do it faster, like you can put it in the chat, like not the approach, like what do you think? Like can we do check, like find all the prime number, check or like find all the prime numbers less than n, like faster than checking each numbers from 1 to n. So what do you think? Okay, someone is saying that like find GCD of each pair. So we are not discussing about co-prime. So like GCD of each pair is not something that we would do. Uh, yeah. So uh, again, like if you are saying that maybe like check for each numbers maybe from 1 to n minus or like for if I is from 1 to n, then for each I check if everything, every number less than I, like see the GCD and check. That is basically the naive way of doing this, like we did. Okay. Yeah, so Ashima says like Sieve of orthogonous. So yeah, we can do Sieve of orthogonous. Like it's a technique that actually helps us to find all the prime numbers less than n. So yeah, hope my screen is still visible, Nija. Uh,
Yes, Ashwin, it's visible.
okay, yeah. So let's see like Sieve of orthogonous. So let's see the numbers from 1 to 25. 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, so now we have to find all the prime numbers less than 25. So let's just exclude 1. So why do we exclude 1? 1 is neither prime or like, it's a composite, it's a special number. So let's exclude 1. Let's 1 be on its own. Now 2 is a prime. Now, so we check 2. Let's take 2 to be prime. Now go to all multiples of 2. Say that like it's not a prime. Like, so why is it not a prime? Because like it's a multiple of 2, right? Like, so it's not a prime. So yeah, like let's strike off 4. Then like 6 is the next multiple. 6 goes. 8 goes. 10 goes. 12 goes. 14 goes. 16 goes, then 18, 20, 22, 24. Okay, now let's see. Okay, now 3 is a prime. Now let's go to multiples of 3. So next multiple of 3 would be 6. That's already stricken off. Then like we have 9. 12 is gone. 15 is a multiple of 3. Let's strike it off. Then 18 is gone. 21, let's cut it. Then 24, it's gone. So now 5 is a prime. 5's next multiple is 10. It's already gone. Then 15, 20. Okay, I strike off 25. So now we can go for 7 and 7's multiple. But then see, 7 into 2 is considered, 7 into 3 is considered, 7 into 4 is considered, 7 into like 5 is considered, and 7 into 6 would have been considered. Like, so why is 7 into 2 considered? Because like we already did for 2, so that would have been taken off, right? Like we would have already did for like 3, would have done it. Like, so all the numbers less than 7 we would have done. So if that is the case, then like the next multiple of 7 that we can actually strike off would be 7 into 7, which would be actually outside this range, because like square root of like 25 was 5. So 5 into 5 itself was like 25. So we don't need to actually do for like 7 into 7. So we only need to do this like till the numbers which are root of like 25, and like find all its multiple, find all its multiples, strike it off. So 2 is a prime, 3 is a prime, 5 is a prime, 7 is a prime, 11 is a prime, 13 is a prime, 17 is a prime, 19 is a prime, 23 is a prime. So is this clear? Like, is this approach is clear? Like, so this is like something that all of you might have done in school. So it's called Sieve Factorisation. So this is like one efficient way of like finding all the prime numbers, less than the number n. Now let's try coding this and solve the question prime or not. So if this is clear, I'll all of you can maybe put a thumbs up or like raise your hands to say that okay, like this approach is clear. Okay, cool. Now let's try coding this with the question prime or not. So I have not written any code. Like, let's try and code this together. So if you find any mistakes, feel free to point it out. Give me a second. Okay, yeah. Now okay, we have like 10 power 3 cases and like 10 power 3 numbers. So let's find all the primes till like 10 power 3, pre-process this. So vector pool so I assume all the numbers to be prime initially, and like whenever I encounter a multiple or a number which is not prime, I'll strike it off. I'm assuming everything to be true, which means that like if prime of I is true, I'm saying that like ith number is prime. So whenever I find that like I is not a prime, I'll turn prime of I to be false. So initially I change, like keep everything to be true. Now let me do prime of 1 is equal to false, which I did. Now for int I is equal to 2, I star I less than or equal to 10 power 3 plus I. Now for int j is equal to I. No. Now I have to check if this is a prime number. If not prime of I'll do continue. Like I don't want to find non-prime numbers multiple. I am only finding multiples of like prime numbers. So what I do is in j is equal to I, j less than or equal to 1000, j plus equal to I. So j will be my multiples of I, which I'll mark. So this should not be I because I is prime. I don't want to mark this as false. So what I can do is like 2 star I. But then like as we discussed, like we don't have to actually start from 2 star I. We'll be starting from I star I. So 2 star I, 3 star I, like every multiple of like I, which is the multiplication factor less than I would have been already considered. So j will be I'll start from I star I and j less than or equal to like my total number. Then I do like prime of j is equal to false. Now let me do one thing. In t c in t while t minus minus int n c in n, if prime of n, I'll do cout prime, else cout not. Okay, so that's done. Now let's just test run it, see if it works. Okay, yeah, it worked. Are you guys familiar, like understood this code? Like, so we can also do a full submission, see if it works. So is this code like, did you understand these 2 loops? Yeah, so this is correct. So the time taken, like, so this is like, super fast. Maybe you can go and compare with the solutions that you wrote with the other approach, see the time taken and the time taken for this. Like you can do the comparison and see, like, so this is definitely faster. So if you all understood this, this piece of code, maybe raise your hand or like drop something in the chat. Okay. Now let's, do the time complexity analysis of this prime sieve. Like, so what is we did the time complexity the other day, right? Like, so let's see like what is the time complexity of this prime sieve. So for the outer loop, that is your loop of I is going from 2 to root n, and out of this you are only going till like for every number, for 2 you will go n by 2 places, then like next you will go n by 3 places, then you will go n by like 5 places, similarly you will go n by root n places. So if you take n outside, you can like think of it as like 1 by 2 plus 1 by 3 plus similarly like maybe 1 by n. So we saw that like this is log n from previous sessions. So this would be log n, and like actually we don't have n outside, like we only have root n. So we can think of the complexity of pre-calculating all of this would be like kind of root n log n. This is pretty fast. So this is very rough analysis of the time complexity, but then like this is to give you a rough idea like how you can do the time complexity analysis. Now I have a question for like each of you. So can you modify this algorithm? No, let me ask you something like, so are you familiar with the concept of like prime factorization? What is prime factorization? Or prime factors? You can put it in the chat. What do you think? Like, what is prime factorization? What are factors of a number? Like, so factors of a number are the numbers that divide a number, right? So, like for 10, the factors are 1, 5, yeah, like so 2, I missed 2, then 10 itself. So these are the numbers that divide 10. And if I see the prime factors of 10, like so out of all the factors, I'll delete all the factors which are not prime. So that is like 2 and 5. So 2 into 5 is like, prime factor. But then like this is not the definition, I made a mistake. Basically, prime factors are the prime numbers. If I multiply all of those prime numbers, I get the number. For a number n, the prime factorization of it can be written as like p1 into p2 into p3 into so on, like p n, where all of these numbers are prime, and like product of this is equal to n. This is the prime factorization of a number. Basically pi of p of I goes from 1 to n, 1 to small n, equal to capital N, where n is my number. So this is the prime factorization of a number. So there will be situations where you have to prime factorize a number. So which is the easier way of doing a prime factorization? Like yeah, dividing number using prime numbers. Like so that is like the way of easier way of doing prime factorization. So imagine that like I have maybe 20. I'll do prime factorization of 20. So one of the ways of doing prime factorization of 20 is I keep dividing 20 by prime numbers till it becomes 1. So first prime number is 2. So I divide 20 by 2. I can divide it by 2. Like so my number becomes 10. Now I again divide 10 by 2. So it becomes 5. I get one more 2. Then I have 5. 5 I cannot divide by 2. So I stop dividing by 2. Now I divide by 3. I can't divide by 3. So I go again and try dividing it by 5. So when I divide 5 by 5, I get 1. I include 5 to prime factorization. So this is the prime factorization of 20. So for this, like you have to go a lot, right? Like you have to keep on dividing by prime numbers to get the prime factorization of a number. But what if we can use the sieve to do the prime factorization faster? Do you think we can use sieve to do the prime factorization faster? Do you, if you can find a technique or like modify the sieve, can you tell me like if you can do it? You can put it in the chat if you have any approaches. If you think you can do it, like tell me you can do it. If you know the approach, you can also put that in the chat. So otherwise, like I'll tell you how to do prime factorization of a number, like using the sieve that we did just now. Okay, looks like nobody knows it. So yeah, let's again consider uh, the numbers 1 to 25. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, now let's do this thing. Imagine that like so this is all one based indexing. So like each a of like index first index has 1, second index has 2, third index has 3, fourth index has 4. Like so all the ith index has like I ignore the zeroth index. So ith index has like number I in it. So imagine that like if I is equal to a array of I, this is my array A. So if this is the condition, I take this number to be prime in this condition. And what I am storing in this array is basically the largest prime number that I can so if the largest in A of I will store the largest prime number that divides I. So if I is a prime, uh, I is a prime. If I is a prime, then like A of I should be I, right? Like so, this condition should hold. So that is how instead of storing true or false, the check like maybe if it's a prime or not, I'll store the largest prime number that divides I. So if I is a prime, the largest prime number that divides I would be I itself. Is that clear? If it is clear, you can maybe raise your hand or like put it in your chat. Okay, yeah. So that's that. Like people are raising their hands. So since that is clear, let's go ahead. Let's do this thing. So now again I exclude 1, like 1 being special. I don't consider 1. Like let 1 go away. Now let's go to 2. So the largest prime number that divides 2 is like 2 itself. Now let's go to 2's multiple. See, not largest prime number. Let's see the smallest prime number that divides. Like so. Sorry for the like confusion. Yeah, like so. Okay, fine. Like yeah, let's store the largest prime number only. Like so, we can do it with the smallest prime number or largest prime number. Like let's do it for the smallest prime number. So no, sorry again. Like so, I said largest prime number in the beginning. So let's stick to largest prime number. We do the largest prime number. So the largest prime number that divides 2 is 2 itself. So let's go to 4. So the largest prime number that divides 4 is not 4. It's 2's multiple. So for time being, I'll say 2. Then for 6, I'll say 2. For 8, I'll say 2. For 10, I'll say 2. Then for 12, I'll say 2. For 14, I'll say 2. Some of this might be wrong. Like so, for 10, like 5 is the largest prime number, but then we'll fix it in a bit. So then we go 16. We'll say 2. For 18 we'll say 2. For 20 we'll say 2. For 22 we'll say 2. For 24 we'll say 2. Now for 3 let's go to 6. So 6 we have 2 here, but then like 6 3 also divides it, like so 3 is also a prime. So let me update it to 3. Then 9 I'll say 3. Then 12 I'll say 3. 15 I'll say 3. 18 I'll say 3. Then 21 I'll say 3. 24 I'll say 3. Now let's go to 5. So for 5, 10 I'll say 5. 15 I'll say 5. 20 I'll say 5. 25 also I'll say 5. Now imagine that like now you want to do the prime factorization of a number. So if it's a prime number, like so the index will match, this condition will match. So if this condition is matching, it's a prime number. So the prime factorization of that number would be like there will be only one number which will be a of I or like I. But then like imagine a number which is not a like prime number. How do we do the prime factorization? For example, take 24. So go to 24. So what you see? You see 3. Okay, like so take 3 as like the first prime factor. Now do 24 by 3. Like so what is 24 by 3? Like 6, not 6, right? Like 8. Yeah, 8 into 3 is 24. So let's go to 8. Now you see 2. So I take 2. Now I go to 8 by 2. 8 by 2 is 4. Again I see 2. So I take 2. Then I go to 2. Again like 2 has no like it's a prime itself, like so I again include 2. So that is like 3 into 2 into 2 into 2. So this is nothing but the prime factorization of 24. So 24 is equal to 3 into 2 raised to 3. So this is the easy way of doing the prime factorization. So now the pre-computation or like making this sieve will take the same time as the sieve that just says if a number is prime or not, but then it's giving us the additional information which we can use to do prime factorization. So like can someone think like what will be the time that, so imagine that if you are provided with this table, what is the worst time complexity or like worst time worst number of operations that you take to do the prime factorization of a number? Like what do you think, like how many times you will have to divide to prime factorize a number? So you can give your answers in the chat. Then I'll give you like the analysis or like time complexity. Any guesses? Like so, how long will it take for a number out of this to be prime factorized? How many operations will it take? Is it linear time? Or is it like maybe square root of that number? Like how many operations will it take? Any guesses? I think there are no guesses. So let me ask this question: like, did you understand this approach? Like how we are prime factorizing using Sieve? If you understood this, like please raise your hand. If not, I can explain again. Do you want me to explain this again? Okay. Yeah, so let's just erase this. So so this is cell number 1 which has 1, then cell number 2 which has 2, cell number 3 which has 3, cell number 4 which has 4, cell number 5 which has 5, 6 which has 6, 7 which has 7, 8 which has 8. So the what is in the this like subscript is the index. Imagine that is the index. So Yeah, so now imagine that like each of the index has like that number itself. Like so a of I is equal to I. And we say that like if a of I is equal to I, like I is prime. So if this condition holds true, then like I is prime. So now let's start building our run our sieve or like do the process and like get it do the pre-processing. So let's go to 2. Now go to 2's multiples and I say that like okay 4 is divisible by 2, so instead of writing 4 I'll write 2 here, like so I write 2 here. Then like for 6 I write 2, for 8 I write 2, for uh, for 10 I write 2, 12 I write 2, 14 I write 2, 16 I write 2, 18 2, 20 I do 2, then 22 I do 2, 24 I do 2. Now for 3 I go to 3's next multiple, that is 6. I put 3 here, then the next multiple I put 3 here, the next multiple I put 3 here, then next multiple I put 3 here, next is 18 I put 3 here, 21 I put 3 here, then 24 I put 3. Now for 5 like 10 I put 5, this is a 5, 15 I put a 5, 20 I put a 5, and 25 I put a 5. Now let's try and prime factorize 24 using the prime sieve. So before I do that, like did you understand this process? Instead of like marking true or false, each of these indexes hold a number, and if the index I matches like the number in index, then like it's a prime. So that is the condition for checking a prime, and like it holds this numbers. So is this clear? If it's clear, yeah, like so. Okay, this is clear. Now let's try and do the prime factorization of 24. Now go to the index 24, check if 24 is equal to 3. It's not equal to 3. So basically that means that like 24 is not a prime. So let's take the number written in the index 24, add it to the prime factorization. I added 3 to the prime factorization of 24. Now I divide 24 by 3. What is 24 by 3? It's 8. So let's go to 8. Now I see that 2 is there. Like so 2 is not equal to 8. So 8 is also not a prime. So I write 2 to my prime factorization. Then I do 8 by 2. 8 by 2 is 4. I go check here. Like so here I have 2 in the like array. So 4 is not equal to 2. Again 4 is not a prime. So I write 2 again. Then like I do 4 by 2. So finally I reach index 2 where I have 2 equal to 2. So which means that it's a prime. So I stop like going further. I also take this 2 included. So this is like 24 is equal to 3 into 2 into 2 into 2. So which is 3 into 2 raised to 3. So this is the prime factorization of 24. So is this clear now? This is how we can use this table to find the prime factorization of any number from 1 to n. Okay, yeah. So now this is clear. Now the question is like what is the worst number of operations or like worst number of hops? So in this case I hopped from 24 to 8, then from 8 to 4, then I from 4 to 2. So I did like 3 hops. Maybe yeah, like so I included this also. Yeah, 3 or like you can think it of like 3 or 4 hops. So how many times do I have to hop, or like how many times do I have to? So yeah, like let's say that like we'll only stop when we reach 1. So that is like if that is the case, like we got like 4 hops. So or 4 times we divided it. So like how many number of times we'll have to divide for any n? Like so what is the worst case like when we have to divide, so that like we'll find the worst case complexity of factorizing a number, prime factorizing a number. So for 24 it was 4. So for any n, like, can we say a generalized number? Maybe it's root n, or like maybe we'll have to divide n times. Like, so what do you think? Like, how many times we will have to divide it? Do you have a guess? So pre-processing of this is same as the complexity that it takes to build prime sieve. I'm asking for like just the prime factorization part of it. So I think you don't have a guess. Like, so I'll do the thing. So the worst case is like when all the prime factorization. Okay, you said like n root n. Like, so no, it's not actually n root n. Like, so for a single number, like prime factorization is very faster. Like, it's not root n. So when we have we can do like root n log n for like building this. Root n log n for building this whole thing, and that I'm not including. Like, so I'm just asking, like, if this is built, what is the complexity of like finding answer for like one factorization? So worst case, n can be a power of 2. So it can be 2 raised to x. So in that case, like, we'll need like to keep on dividing it by 2 till it becomes 1. So we'll have to divide it by x times. So if we know that like n is 2 raised to x, then like x is equal to log of n, log to the base 2 of n. So in log n time, we can do the prime factorization of one number. So to build this for like all the number under n, it takes like root n log n. Then like for prime factorization of all the numbers would take for each number I have to go through iterate like from 1 to like n, or like 2 to n. Then each number I can do the prime factorization in log n. So I can do prime factorization of n numbers in n log n, which is like log n is much smaller than root n. So n log n is basically much better. Like, so it's very fast. So let's go to the code snippet that we had, and then let's modify this. So instead of like making this boolean, I'll make it int. Now I'll remove true. So instead of true, the condition that I have is I have to first assume that like all of it is prime. So for int I is equal to 1, I less than or equal to 1000, I plus plus, prime of I is equal to I. I assume that all of the numbers are prime. Now here my check would change, right? Like, my check would be, if it is not a prime, then like a prime of I would not be equal to I. Then I continue. Then instead of false, what I put is j. Now here also the prime check would change. It would be if prime of not n is equal to n. Let me test this. Okay, it gave me a wrong answer. Okay. So let's see, where did I go wrong? Yeah, so this was the mistake. So 12 instead of like j, it should have been I. Still wrong answer. Yeah, the condition is so if to be prime, it should be prime of n is equal to n. Like, it should not be the other way around. Like, that is the not prime condition. So let's do the test again. Yep, it worked. So this is how we modified to build the prime. So you can think of like how will you do the continuous division to check if like how to get the prime factorization of that. So I'll leave that to you as an exercise. Using this prime sieve and like the method that I explained, you can do the prime factorization of a number faster. So that's it for like today's session. If you have any questions or doubts, you can post it in the chat or like in the Q&A session. So I would recommend you to go to this question like from prime or not from the practice round and try solving it using the prime sieve. So I'll wait for a couple of minutes if you have any questions. Otherwise, we can break for today. Best of luck for the semi-finals. Looks like yeah we don't have any doubts. So yeah, thanks everyone for joining. So once again, like best of luck for the contest. Bye everyone.